And then the question is, how do we evaluate the performance of these transmission line or antennas in the case of a frequency diverse imaging? So we should define a figure of merit in this a new application scenario. The first way is we can directly evaluate using this measurement matrix H, because this H has all the information of this electromagnetic structure. We perform the singular value decomposition on this matrix. So decompose into three matrices, U, sigma, and V. The singular values is stored in this sigma matrix as the diagonal entries. So this figure shows a singular value distribution of a typical example. So it has 100 measurements, but we can see here the non-zero singular values are less than 15. So this means although you have 100 different measurements, the effective measurement is only 15. Most of these measurements are redundant. They have zero singular values. So we can use this SVD analysis to evaluate the effective number of measurements for the electromagnetic structure. We can further define our sensing capacity in analogy with the MIMO communication using the channel capacity. So here, lambda is the singular values that are calculated using the SVD analysis. The P divided by N is the signal to noise ratio. So we can define this capacity C here. So we establish a one-to-one correspondence between the MIMO communication and the imaging and the sensing. So here, the channel matrix in communication corresponds to the measurement matrix in imaging. Okay, so these non-zero singular values in communication means the independent channels for communication. So here, in the case of imaging, all of these non-zero values means the independent interactions between this antenna and this object. So this vector in this U and V corresponds to the channels in the communication. In the imaging case, the vectors here corresponds to the interactions. Okay, so we have a unified point of view to look at the communication and imaging. Then let's look at the relation between the sensing capacity and the dispersion and the loss. So here we show three different transmission lines with different dispersion. So TL1, TL2, and TL3, we increase the dispersion from 1 to 3. So this shows the dispersion curve. The dispersion increase from 1 to 3. And we can see the mode number will increase as we increase the dispersion, and also the capacity will increase. So this shows that the sensing capacity is proportional to the dispersion in this frequency diverse imaging application scenario. And this figure shows the effect of loss. So the first figure shows the lossless case. If we don't have any loss, this figure shows the singular value distribution. And as we increase the loss here, we can see the singular value drop. So the capacity will drop, right? Further increase the loss leads to a further drop of these singular values. So as a figure of merit, so we need to enhance the phase dispersion of the transmission or antennas. And meanwhile, we should decrease the loss. For the antennas, usually we wanted to describe this FOM using some far field parameters, for instance, the beam angle. So here we also define a scanning rate. It is defined by d theta divided by d omega. D theta is the beam angle change, right? So this scanning rate will tell you the sensitivity of this angle with respect to the frequency. After some derivation, you will see that this scanning rate is proportional to the phase dispersion of this transmission or antenna. So finally, we can use the scanning rate as a figure of merit because it is proportional to the phase dispersion.